What you see on the Rigol DSA-815 here is a transmission measurement from 5 megahertz on the left to 900 megahertz on the right, and the device we're looking at is a low-pass filter, but it's a 75 ohm low-pass filter intended for use in the cable industry. And I'm using this to illustrate how you can do transmission measurements on non-50 ohm systems using the nanoVNA. So why am I using the Rigol? Well, I just want to show you what the Rigol sees in terms of the frequency response. There's a marker at this point which is right at 380 megahertz, which is what the filter is marked for. It's a 380 megahertz low-pass filter. And so here is the marker, and you see we're down about 4 dB at 380 megahertz. Now, the system that I have is going to look a little bit unusual. Let me describe what you're seeing here. This is the tracking generator of the Rigol. It's coming through a mini circuits 50 ohm to 75 ohm matching pad. Then it's going through the filter, and then this cable is connected over to this mini circuits matching pad, which transforms it from 75 ohms back to 50 ohms, and that then goes into the input of the DSA-815. So what we're doing is a transmission measurement on a 75 ohm device using a 50 ohm test set, in this case a 50 ohm spectrum analyzer with tracking generator. So now let's take a look at what we get on the nanoVNA using a somewhat similar setup. And so here on the nanoVNA, this is the H4 that I'm using. I use it because it has the larger screen, so it's easier to photograph. But and I found that the H4 is becoming my favorite nanoVNA. It doesn't go all the way to 3 gigahertz like the V2 does, but I very seldom do measurements above about 1 or 1.5 gigahertz, so the H4 is fine for me. I like having the V2 because I can do 2.4 gigahertz measurements with it, which do come up from time to time because, of course, that's where the ISM band is, where Wi-Fi and at least the lower frequency Wi-Fi and so on. Anyway, here is the same filter, and you notice that the let's see. Yeah, there's a 380, it's about 380 megahertz is where the marker is. And you see, once again, it's a low-pass filter. Now, it does have some passband here, so some ripple in the stop band. Okay, so how in the world do you do this? Well, let's take a look first at the configuration. And over here, and as you see, what I have done is I have inserted the same mini circuits matching pads. So what we are actually measuring is just from here to here, because I calibrated using this set of 75 ohm short open load that I have talked about in a previous video. Now, this is a 75 ohm set, not a 50 ohm set. The difference is that the short is on an F connector, which is a 75 ohm. The open is just an F connector with nothing on it. and the load is a 75 ohm load with the F connector on it. So I calibrated this at this point. In other words, at the 75 ohm point, if I zoom in on the mini circuits, you will see there that the right hand, or the kind of upper right hand side, is the 50 ohm side, and the lower left hand side is the 75 ohm side, which is of course the side that's connected to the filter. And then on this one, you notice the 75 ohm side is connected to the filter and the 50 ohm side is connected to the VNA. So that is how we measured this filter response. Now what I would like to do is try one more device and then go ahead and close this video. Now we have this two-way splitter that is supposed to work from 5 to 900 megahertz, and it's supposed to be relatively flat over that range. So let's take a look at the and once again, I'm still using the matching pads on each side. So 75 ohms in the middle, 50 ohms out to the VNA on both sides. And here is the magnitude plot. This is log mag, notice from 5 to 900 megahertz. And once again, the marker is still set at 380 megahertz, but you can see over the range, it starts out with virtually no loss at at 5 megahertz, and loses, I think this is 10 dB per division here. I'm not sure exactly. We're not trying to actually characterize this device, just more illustrate how to use a VNA. But it appears to me that there's about 7 dB of loss relative to 5 megahertz out at 900. So it does show that we can use 75 ohm systems. There's a couple of ways to do it. Really expensive vector network analyzers, you can literally set the impedance of the device, both the transmission side, in other words the S11 side, and the S21 side, to pretty much any value you want. With a unit like the nanoVNA, that would be rather expensive because it involves relays and attenuators and all kinds of things to calibrate it, which have to be built into the instrument, and that's one reason that they cost so much, the bigger instruments. But nonetheless, if you're willing to do a little bit on your own, and if you're willing to accept amateur level accuracy, you can do this on your own nanoVNA, and you're not limited to 50 ohm devices. You can use, in this case, a 75 ohm. If you're working with a 300 ohm system, this will also work, but you will need matching pads of some kind. Now, I use these matching pads for a lot of things where I match to 75 ohms, and so I don't consider them an extra expense. But if you do have a nanoVNA and you want to use it on a 75 ohm system, remember that you are going to have some way to transform. Now, in an earlier video, we did just S11 measurements looking into the input port of this. We didn't do transmission measurements, and a viewer asked the question, if you do transmission measurements and you've calibrated at this end to 75 ohms, isn't the input impedance of the nanoVNA on the S21 port, or channel 1, 50 ohms? So don't you have to do something there? And the answer is yes. You have to transform from 75 ohms back to 50 ohms. So I hope this video has been interesting and maybe a little bit informative. But I think at this point I'm going to maybe move on to, in a slightly different direction, maybe compare the nanoVNA, the V2, to the VNA Tiny Plus that I reviewed a year or so ago. At any rate, stay tuned, stay safe, and have a nice day.